Hello, this is Ana Doblas from University of Memphis. Welcome to the first module in this NSF workshop that is gonna be, I already say it's funded by NSF, but it's related with my NSF career project. So in this workshop, we're gonna talk about imaging modalities and in more particular about digital holographic microscopy, kind of telling you the optical configuration, the reconstruction methods, and what is new, that is the application of deep learning methods to reconstruct it. So in this workshop, I'm super happy that I have my partner and collaborator, Carlos Trujillo from EAFIT University in Colombia. And we're gonna have an invited speaker for the next module that is gonna be about quantitative phase imaging. So anyway, thank you so much. I hope that you like it. So the first talk is about talking about the difference of the imaging techniques from the macroscopic or medical related imaging techniques to the nano. So what is the learning objective that you need to learn? So at the end of this module, you're gonna need to be able to differentiate the different type of imaging modalities and what is the trade-off. So in other words, like you cannot don't use any imaging modality. Like depend on your sample, depend on your application, what you want to do, you might select different type of imaging modalities. For example, if you are thinking about using something kind of non-invasive, the whole body, so those are the medical related imaging modalities. So the resolution obviously is gonna go to the lower 100 millimeters up to the 10 centimeters. So we can detect like cysts and some organs. Later on, we are moving to the microscopy world, and within the microscopy, there are a lot of imaging modalities up to going to the STAT, which we got in a Nobel Prize in Chemistry in 2014. And then obviously we have electron microscopy that we are not getting covered. So let's start with the first medical related imaging modality. That's gonna be the positron emission tomography. So this is where it's gonna happen is what we're gonna measure is the metabolic activity of the cells within your body. So we're gonna use some reactive materials and they're gonna kind of bind to certain tumors or proteins. So the camera is gonna be able to detect what is gonna be the positron emissions. It's super important, or it has been widely used for brain and heart conditions, and we can kind of analyze the biomedical changes across the body. The next imaging modality is the MRI, so the magnetic resonance imaging. So what that creates is gonna give us detail of our organs and tissue within the body. So what is gonna happen is like we're gonna use a really powerful magnet, and magnet is gonna align the water molecules that we have in the body. So we're gonna send radio wave, right? So the magnet is gonna be on and off. And what we're gonna be able to see is like the shift of the water molecules when the magnet is on and off. So the MRI, it's a difference. It's like a crosstalk image of that shift of the water molecules. The next one is gonna be the ultrasound. Okay, so the ultrasound here, and probably most of us we are familiar with this one. It's a high frequency sound wave that they are sending to our body. So we use a transducer and we are gonna put it on touch with our skin, and we're gonna see kind of like the signal that get reflected across the body at the different levels. So the resolution here is not super good, but it's still gonna be able to discriminate. Like definitely we are not in the micron order. And to get the best performance of the ultrasound imaging, we need to put the gel within the transducer at the skin, so we know for sure that we have the highest transmittance of the signal through the skin, and it's based on the amplitude of the reflective wave. That's what we're gonna learn. So the next one, I love this one because it's super related with digital holographic microscopy. In fact, they are based on the same principle. So it's optical coherence tomography. So it's what a lot of people call kind of like the optical version of the ultrasound. And the thing is that it's kind of like a reflection base, but it's different. So in this particular system, it's based on interference. So we have two beams that they're gonna to be together, and the beam, and this is super the key and the difference from DHM. So the beam, the light of beam is coming from a source that the spectrum of the source is broad. So that's what you're gonna learn as a temporal incoherent or like low coherency. So every time that you hear like incoherent, it might be temporal or spatial. If you want to have interference, it needs to be spatially coherent. But for the OCT, we don't need to have temporal coherence. So this is the basic OCT system. And I took this from my postdoc advisor, UNC Chapel Hill, like Dr. Oldenburg. So what is gonna happen here is like, it's based on a microsound interferometer. So this is the object beam, and this is the reference beam. And in the reference beam, that's the temporal base OCT system. Let's assume that we have a mirror. And the mirror, we can move it at different planes. So every position of the mirror is gonna be only having interference with a particular depth of your sample, right? So that's where we say here 1, 1, 2, 2. So those are particular positions that we're gonna have. So the photodetector, what is gonna happen is we're gonna get the signal of the interference, and that signal is gonna be related with the reflectance of the sample that we are imaging. The biggest concern about OCT, so we can image, it can be up to a couple of millimeters. The resolution, it really depends on the optical system that you are putting. Like definitely if you have a high numerical aperture lens in front of the object, your thickness is gonna be less just because the working distance, you're gonna hit the lens or the objective lens. But you have a wide variety of making the optical configuration to kind of match the application that you want. It's widely used, so there are commercial systems. They are not used as the temporal base, it's the spectral base. So what that means is you don't move anymore the reference, but you are having a spectrometer behind. So every kind of like position of your depth, it's encoded in a different wavelength, and that's what your camera records. Your camera records the wavelength spectrum, and then you make an inverse Fourier transform to go to the depth information. And it kind of has been really used for glaucomas and kind of like analyze the eye. That's super important with people for diabetes. All right, so this is the best. So optical coherence tomography, because it's a temporal incoherent source, they have super nice axial resolution, like up to 1 micron, but the lateral resolution is lower, like can be like a tenth of, like a dozens of microns. So, but we are not going below, we are not going to the micrometer or below the micron. So for that one, sorry, yeah, sorry, I forgot to say, but the problem with the OCT is that you need to do a scanning. It's kind of like a point base. So you need to scan your sample. So wide field microscopy, which is the basic microscope that you're gonna have, it's not confocal based. So you illuminate your sample with a uniform beam, like a plane wave, and the camera kind of gonna record the light scattered by the sample. So there are different modalities. You have here like the regular wide field image, but if your sample, especially like biological samples, they have a low absorbance, so you're gonna see that they are almost transparent. So a lot of time you want to stain your sample with fluorophores so you cannot detect the fluorophores. So, and that is just to make sure like so what is gonna happen is like you're gonna, for example, illuminate with green color, green wavelength, and there you're just gonna only collect the excitation light, the emission light. So the emission is gonna always happen in a longer wavelength, so that's gonna be red. So here in the imaging space, you might want to put a filter, a bandpass filter, to make sure like on the camera the only thing that gets recorded is the emission information and not any excitation. So that's why the background of the images are kind of black. So there are different types of microscopes right now. What we use typically, and this is what it's mounted on the commercial microscopes, are like you have an infinity corrective beam. So that means that the image of the object is sent to the infinity, but because we don't have access to the infinity, you put a tube lens, so that infinity image gets the position in a finite plane, which is gonna be your image plane, but this is where you put the camera. So this is kind of like the basic configuration of a microscope. Obviously, in a commercial microscope, we have so much lenses, and in that relay system, just to probably magnification, it's 1 because we just want to keep the magnification of the objective lens, but it's kind of just put the things in a place where we have access. So the biggest concern, so wide field microscopes are super easy to implement. So the resolution goes to 400 nanometers with a high numerical aperture, even 200 if we use an oil immersion lens. We have a 2 lateral or translational image like X and Y. So we don't need to scan the point, but the biggest concern is that even that the area of your sample it's not focused in the image plane, you have the information of the autofocus information. So that like means that they don't have optical sectioning capability. And the other concern is that if the working distance is long enough, you can just actually scan the different planes of your object. But there's gonna be a limitation because the spherical aberration. So like you cannot definitely go to microns. So this is not for thick samples. So confocal microscopes, what they are meant to solve is the optical sectioning capability. So right now, what we are illuminating, so we have here a 3D object, right? So we are illuminating a point, and that's okay. That looks like the OCT system. So it's point-based illumination. But what is super important and is the key of the confocal microscope is point-based detection. So this plane of the object is completely conjugated with the pinhole plane. So only the light that is focused here is going to go in through the pinhole. So if you have an object that is in another different plane, so now the beam is going to be broader and it's going to be blocked by the pinhole. So that's how we gain the optical sectioning capability. So we cannot block, the pinhole blocks the autofocus information. The biggest concern is that it's point-based, so it's going to take more time. And if you are using fluorescent, you may have photobleaching of your cells. The resolution, like the pinhole, so obviously if you don't have the blur information coming from the autofocus sections, that's going to improve the contrast of your images. So that's going to help in the lateral resolution of your microscope. But however, that resolution is not like double, like in the next technique that I'm gonna discuss to you. So let's assume that the lateral resolution is roughly the same as the microscope. So mostly it's gonna depend on the objective lens that you are using. And as I was saying here, like the biggest is you have optical sectioning capability. So if you are imaging on a stack of pollen grain, so you roughly don't see anything in the wide field image, which is the top set of images, because just the out of row information is the information that is most keeping in all the transverse section of the pollen grain. But with the confocal microscope, you're gonna see the different part of the grain that's gonna get focused when you are scanning it. So that's really gonna give you a better idea about your 3D volume. Again, so I'm talking about 3D volume, so the next question is, what is about the thickness? So here the biggest concern of confocal microscope is the working distance. Like usually they are using high NA numerical aperture. So the working distance are gonna be definitely like around 0.6 millimeters. So you need to make sure like you cannot probably go more than 600 microns because you're gonna hit the objective lens. So the depth is gonna be kind of limited by your objective lens. So this is the next step. So confocal microscope, you need to do the 2D scanning. Lateral resolution is slightly improved than the wide field, but not a lot. But you have optical sectioning capability, which that's super nice, and that's what most of the people care. But again, the resolution, it was not the best. So what we can do to improve it? So that's the structure illumination microscope. So the structure illumination microscope, they do these two problems at the same time. So they increase the resolution of the microscope, they double lateral and axial resolution of the microscope, and they reduce the autofocus information. So the both problems that the wide field microscopy they have, and only one problem was tackled with the confocal microscopy, a structural illumination microscope was able to improve it both at the same time. So how we do? So let's assume that you have an object, right? And your object, in this case, I put it in the XZ direction, but that's not matter. Let's assume that it's Y, XY, but it has an infinity number of frequencies, right? So it's like a high detail object. So when you make the Fourier transform, you analyze the frequency content, and it has a broad number of frequencies. But when you go to the response of your system, the frequencies are getting cropped by the optical transfer function of your system. And in that case, for the wide field microscope, we have a bow tie, right? So all those frequencies, they're gonna crop, and we're only gonna have here a single frequency in the middle. So the only one that they are going past is the ones going in this line. And if you have a single frequency, you have a delta, and you go back to the real space, you have a uniform image. So you see that all the frequency content that we have in the object, they have blocked by the system response, right? So that's why we are cropping the resolution of our system. So what is going to happen? What is the paradigm that structural illumination they do? So they shift the spatial content of your sample. So what is going to happen is the following, right? So we have the same object, and the same object has the same frequency. So I'm going to talk more in, I think it's going to be in the module 3. But if you, so for every job, you can talk about the real and the Fourier domain, right? And they are linked to each other. So if you know exactly the frequency, you know exactly the object. So we have the object frequency, and we shift it. And I'm going to show you later how we shift it. But let's assume that you want to shift it in a different area. So now the shifted version of the frequency of the object gets now transferred to your imaging system. But you see that now where it's gonna go in through this line. So some frequencies right here are gonna pass. So new frequencies that before they were blocked, now they are passing. So when we come back to the real space, you're gonna see here more frequency content of your sample, right? And I know like I make this step super fast, but if you see like we cannot go from this Fourier image to this real space. We just need to put the frequencies to the original position and come back. But that's okay because we know how much we have shifted, so we can put that one shifted back computationally. So that's the whole paradigm. So I'm definitely gonna talk more, but a shift in the Fourier domain means just like adding a plane wave. And if we have two plane waves that they interfere, that's a sinusoidal pattern. So the whole idea at the end of SIM is that shifting that we need to have super resolution, that shifting is gonna get by illuminating the sample instead of a regular uniform beam using a periodic pattern like a sinusoid. Alright, so we go here to from 400 we get down to 200 nanometers laterally and around 300 nanometers axially. Biggest concern is that the thickness. Still, the thickness it's definitely around 60 microns in depth. So the structural illumination, the sample needs to be prepared in a microscope. And I'm not sure about the latest results, but if you try to make everything kind of like within a scattering medium, that penalize a lot the structure patterns, so you might not be able to do it. So how are we gonna solve? We want to go to the dozens of nanometers. So for those kind of imaging modalities, they are completely different and we play in a different regime. So those are the super resolution fluorescent microscopes, and within them we're gonna have three. The first two are the photoactivated localization microscope, and the stochastic optical reconstruction microscopy. And what they are based is that you're gonna like tag your sample with a special fluorophore. So every time that you get an image, only a few of the fluorophores are activated. And you put your light on and off, and every time different fluorophores are the ones that you're gonna get activated. So after a broad number of images, you're gonna be able to create your image. So this is like if you go to the video, Wikipedia has like a give about how to do it. So you're gonna see like this is a regular microscope where you have all the blur. So you just put in and on the different lights, and you're gonna get different type of accelerated fluorophores excited every time. So that's how you get your sub resolution image. So STEM plays a different game. So you still get the same lateral resolution, but the game is different. So what STEM has, and that's the system that won the Nobel Prize in Chemistry in 2014. What they do is it's like a confocal microscope in terms of the optics, but they use two beams. So they use the excitation beam and the deflection laser. So there are two beams illuminating the sample. So the deflection beam definitely is wider. So you see kind of like the red one, and then the excitation beam is kind of like going within the deflection. So we're gonna have this kind of like donut shape. And what is gonna happen is like effectively what we're gonna do is like our input response of the system is gonna be narrower. And we just need to, so not all the fluorophores work, because we need to kind of like select which kind of the fluorophores are gonna be activated or not. So that's how they play. So the SPAM and the STORM, they were like statistics, so statistical methods, and the STET is deterministic because they use these two illumination. So I hope that this is, so I forgot to say before, but the PAM, STORM, and STET, the lateral resolution is super good, but still the sample needs to be prepared, kind of like really thin. So that's kind of like what is the trade-off. What is your sample? What is the resolution that you want? And kind of figure it out how much of your optical design parameters you can tune to get that performance. So I hope that you are more familiar now with the different type of imaging modalities and the trade-off and how they behave and what is the working principle of them. And keep tuned to the next modules of the workshop. I just want to finish this module thanking our collaborators, the funding sources that we are getting, and every member of the group. Please keep tuned so if you want to learn more about microscopy and digital holographic microscopy.